Hello, my name is Sabrina, and this is my project ByQ, a wearable sonic vibrotactile stimulation and cueing device for individuals with Parkinson's. In Canada, there are over 100,000 citizens with Parkinson's disease. Parkinson's disease is a neurodegenerative disease with no cure. It is a result of nerve cells in the brain that are responsible for movement becoming impaired or dying. A bioneurotransmitter known as dopamine is no longer produced, which disrupts those signals responsible for movement between the brain and the nerves. Symptoms of Parkinson's disease include rigidity, tremors, bradykinesia, hypokinesia, and freezing of gait. Treatment options like medications often lose their effectiveness after 5 years of use, whereas other treatment options like deep brain stimulation are invasive as they require surgery and they aren't always efficient. Current wearable devices on the market to alleviate symptoms of Parkinson's disease are expensive and usually only treat a single symptom like tremors. For example, the Emma Watch, which uses coin cells that vibrates on the wrist to cancel tremor vibrations. These devices are expensive, costing upwards to $4,000 only to alleviate one symptom. When treating gait movement, such as FOG in Parkinson's disease, cueing has shown to have a positive effect within the people with Parkinson's disease, depending on the external signal being produced. These external signals help with walking or swinging of arms. A metronome, similar to the ones played for musical instruments on a piano, are effective auditory sensory device as it helps Parkinson's disease with repetitive motions like 1, 2, 1, 2. Another successful treatment in Parkinson's disease involves a somatosensory system, such as a vibrotactile stimulation using sound wave energy inserted into the brain using electrodes. My project involves the design and development of a non-invasive, cost-effective, wireless wearable device re-engineered from components of a sonic electric toothbrush in hopes of alleviating symptoms of Parkinson's disease, including tremors, rigidity, hypokinesia, bradykinesia, and freezing of gait. I was inspired to use a sonic vibration to produce an electric toothbrush after witnessing firsthand how well my grandmother's sonic toothbrush worked to reduce the tremors in her hand while she brushed her teeth. Literature research proves that the Sonicare 6100 series toothbrush produces 31,000 oscillations per minute, in which that frequency travels through the torsion bar into the bristles of the brush, where plaque can be removed. In designing the engineering steps for ByQ Prototype 1, a Sonicare 6100 toothbrush was re-engineered through 4 sections of development. 1. Detachment, 2. Assembly, 3. Attachment and protection, and 4. Adding the adhesive, or in other words, preparing the product for testing. In the first step, I detached the electromagnets, the PCB, and the housing for torsion bar, and the battery from the inner plastic housing of the toothbrush. Then in step 2, the rechargeable battery was placed into a new AA housing unit. New wires were soldered between the PCB and the battery because the new ones were damaged in the process of step 1. A spacer made of neoprene found in my swimming cap was cut 3 millimeters to optimize vibrational amplitude. This was then placed in between the electromagnets and the permanent magnets because the neoprene can withstand high amounts of compression between the permanent magnet and the electromagnet, which occurs through the constant polarity change of the electromagnets, which is induced by the square wave generated in the PCB. In step 3, the circuitry with the permanent magnet was glued onto a metal plate that was then covered with electrical tape. To determine the frequency produced by ByQ, I used an oscilloscope, which gave me a reading of 256 Hz, also indicating that it produced square waves. That is optimum because to open up the sodium channels found in Fistinian corpuscle, 250 Hz is the optimum vibration. That then leads to actual potential being transmitted along the sensory neurons, which causes an increase in dopaminergic neurons, which improves the motor function. For Prototype 2, to improve reciprocal movements of Parkinson's disease, an auditory stimuli was added. To achieve this, the circuitry board of a mini metronome was attached to Prototype 1, which allowed users to control tempo and volume. To see how well ByQ can be used as a therapeutic device to reduce Parkinson's symptoms, 5 tests were conducted plus 1 survey. The tests include spiral drawing, finger tapping, holding glass, the cellometer test for resting tremors, and freezing of gait through a gait assessment. The survey was a usability survey. ByQ is safe because it operates at 60 decibels, which is below the max allowed level of 85. The 256 Hz frequency range was also determined to be safe because it is similar to virtual reality interfaces used in gaming devices. As a safe device, ByQ was tested on a volunteer with Parkinson's disease who was off medications. The spiral drawing test showed remarkable improvements in fine motor control with less jagged edges, smoother lines, and a larger orbit within. The finger tapping test following a sequence of 1, 2, 3, 4, was calculated to an average of 35% increase in taps obtained when using vacuum. When holding a glass of juice was tested using vacuum, there was an 84% decrease in visible tremors when vacuum was on. To see if vacuum had an effect on resting tremors,
Wow.
an accelerometer was attached to the wrist, measuring motion in 3 dimensions. Data obtained showed a significant difference in tremors when using vacuum. The data shown in the graph appeared more linear and closer to zero, indicating very little motion. During the assessment of gait, when using vacuum, the participants showed longer leg extensions, increased speed, better rhythmic arm swings, and should not experience any increase in gait or pauses in their movement. When vacuum was assessed for its usability, results showed an average 4.3 out of 5 ranking, with difficulties in sticking medical adhesives to hairy skin, which ended up being resolved by placing vacuum in a phone armband with an adjustable strap to the sternum. One of the most difficult challenges in my project was being able to attach the accelerometer to the volunteer during the holding the glass testing. For the future, I plan on attaching a proper accelerometer sensor that is lightweight to the user and will not fall off. All aspects of my engineering goals were achieved. Vacuum is inexpensive, costing less than $150, wireless, non-invasive, and it's a wearable assistive device made from a used stock electric toothbrush, a broken speaker, neoprene from a swimming cap, wiring, a mini metronome, glue, and electrical tape. But what makes this device so unique? Well, it uses electromagnets, 2 of them, plus a permanent magnet to generate 256 Hz of vibrations with enough amplitude to reach deep enough in the dermis and the skin in the sternum bone to reach the posterior corpuscles that only accept high vibrations. In the future, Vacuum should undergo additional clinical testing in Parkinson's disease users. In addition, further prototypes made lighter and smaller should be designed. Vacuum is environmentally friendly as it is developed using materials easily found in electronic waste, and this could provide a life-changing option for creating vacuum for only pennies. Vacuum is the world's first in combining high-frequency vibrations, 256 Hz, because unlike other wearable devices that use low frequency, it uses 2 electromagnets with an adjustable auditory cueing options in the treatment of several symptoms found in Parkinson's disease. Thank you.
I think the hope is on the way. I think I'm gonna be happy, and after all, my beautiful granddaughter is gonna help me. My little doctor. There's a hope for people out there like me that happens. Thank you.